Hello everyone. In this video, we're going to talk about grouped frequency tables. In the previous session, we defined first the on-group frequency tables. Remember that in the on-group frequency tables, in each row of the table, there is only one outcome of the variable, only one value. Now, when we have a discrete variable that has many outcomes, you will use a group frequency table. In addition, if we're dealing with a continuous variable, so again, we will use a group frequency table. So what is the meaning of grouped? It refers that in each row we will have an interval. So that means that there are multiple outcomes of the variable in every single row and not just a single value per row. So for instance, let's check this example. So in a manufacturing company, the workers' productivity was analyzed based on the number of good quality products produced by them in 1 week. Build a frequency table for the number of good quality products. So if we check this variable, for sure this is a discrete variable. It's a counting process. So clearly, this variable it's discrete, but if you notice, there are multiple different outcomes. For example, 21, 22, 24, 29, 32, up to 88. So if we try to assign only one value per row, we will get a pretty long table. Therefore, a better approach will be to group data. That means finding the right intervals per row, so we can group data or aggregate data, and we will get a smaller table, which is gonna be like more easy to analyze instead of a longer table. So before we can solve this example, let's check what are the steps that are required to build our group frequency table. The first step is to find the number of classes. So that's pretty much to compute the number of rows that are required in the table. For that purpose, we will use Sturge's rule, which is 3.3 log n plus 1, where n is the number of observations. And we will round the number of classes to the closest integer value. So once we know the number of rows, then the next step is to find the range. So the range here, it's the distance or the difference between the maximum value and the minimum value. So that's going to give us what is that distance. So we can split that distance in the number of classes that we have. Now, before we split that distance in number of classes, we define the precision, which at this point it's kind of like an abstract concept, but once we are solving the problem, it will make more sense. What is the idea of using this precision? So from now, let's only check the definition of the precision, and again, once we are solving the example, we will discuss with more detail what is the purpose of the precision. So the precision is related to the number of decimals in our observations. So if our original data has no decimals, it's 0, the number of decimals, then the precision is going to be equal to 1. If the number of decimals in our data is 1, that means like, for example, 5.1, 6.3, that is only one decimal, then the precision is 0.1. Now, if there are two decimals in our observations, two decimals will be like, imagine that our observations are 4.12, 5.15. So if that's the case, then we are having two decimal digits, right? Therefore, our precision in that case is going to be 0.01. And we keep adding zeros as we have more decimals. So if we go back to the example, please notice that there are no decimals, 0. Therefore, the precision is equal to 1. And again, as I said, when we are solving the problem, we will get more details about the precision. But I just want to give you like a quick idea of why the precision is important. So when we're building the intervals, it is important because we avoid overlapping with the observation. So thanks to the precision, we will make sure that there is no observation that falls in the limits of two consecutive classes. Why? Because later on you will see that at some step we take the precision and we divide it by 2. So if we divide it by 2, for example, if the precision is 1, when there are no decimals, then the number that we get is zero point 0.5. So we're adding one decimal to our data. Since our original data doesn't have a decimal, then if our limits have a decimal, we don't have like the problem that one observation belongs to two consecutive classes. So that's an initial idea of why the precision is important. Then in the fourth step is where we compute the amplitude. So the amplitude is the distance between the limits of one class. So the amplitude is like how wide is one row of the frequency table. So H equal to the range divided by the number of classes. So this is important. We will round the A value up, and we will consider the precision. So what does it mean of considering precision? So, for example, if we don't have decimals, therefore we get 4.2, then we will round it up, that will be 5. Because there are no decimals, we're considering the precision. Now, if the number of decimals is 1, meaning that the precision is 0.1, then if we get, let's say, 4.23, so we'll round up considering the precision. So since our data has one decimal, therefore we will round it up considering the precision, so one digit. So that will be 4.3. So that's the meaning of that expression, round the amplitude value up considering the precision. Okay, so once we have the precision, then we need two important steps here. So we're going to compute the class limits and the class boundaries. So the class limits are theoretical values. We won't use the class limits in a practical way. It's just like a intermediate step that we need to get the boundaries. So the class limits, first for the first class, so the lower limit is just the minimum value in our observations. Then the upper limit of the first class is going to be the lower limit plus the amplitude minus the precision. And then for the remaining classes from the second row up to the last one, remember that there are C classes, we will use these two equations, one for the lower limit and the other one for the upper limit. So for the lower limit, it's going to be the lower limit of the previous class, that's the I minus 1, plus the amplitude. Same idea with the upper limit, but in this case, it's the previous upper limit plus the amplitude. So in that way, you will compute the lower and upper limits for all the classes in our table. So once we have the class limits, then we can compute the boundaries. So the boundaries will use those class limits. So the lower boundary for the first class is going to be lower the lower class limits. And please notice here that we deduct the precision divided by 2. That's what I said before. When we divide the precision by 2, what we're doing is that we're adding an extra decimal into our limits in such a way that we avoid that an observation from our original data set is going to be located in two consecutive classes. That won't happen thanks to this operation here. All right, then the upper limit, it's going to be the upper boundary, I'm sorry, is going to be equal to the upper limit plus the precision divided by 2. And once we have computed the lower and upper boundaries for the first class, then for the remaining classes, the idea, it's simple. It's just to take the lower limit, the lower boundary of the previous class plus the amplitude, and same idea for the upper boundary. It's just the previous one plus the amplitude. So in that way we will be able to compute the boundaries for every single class. So now let's go over the steps using our original data. So let me add an empty sheet here. There you go. Okay, so let's get started. All right, so let's go over the steps that we just explained. So step number 1, we're going to compute the number of classes, C. For that purpose, we use the Sturgis rule. So remember, it's 3.3 log n, where n is the number of observations in the original data. So in total, there are 110 observations. And to that, we add 1. That's the equation. The equation is right here. So if you compute this value, you will get that is equal to 7.73. And we round to the closest value. In this case, it's going to be equal to 8. So that means that our table will have 8 classes. 8 classes or 8 rows. Next step, we find the range. So the minimum value in our table is 21, and the maximum value is 88. Therefore, the range, which is max minus min, is 88 minus the 21. That's equal to 67. And then we find the precision. So since there are no decimals, remember the table here, 0 decimals, then the precision is equal to 1. Precision is equal to 1, no decimals. Next step is to find the amplitude, which is the range divided by the number of classes. So it's 67 over 8. That's 8.375. And here we're going to round up to the next value, and we will consider the precision. So remember, there are no decimals, therefore I'm going to round to the next integer value in this case, because there are no decimals. So that will be 9. That's the amplitude. So once we have the amplitude, now we proceed to find the limits, and after that the boundaries. So for the first one, so let me show you the equations real quick. For the first class limits, we have for the lower one, minimum value. For the upper one, is just the lower limit plus the amplitude minus the precision. So let's do that. So lower limit is 21, that's the minimum value. And now the upper limit for the first class is going to be the lower, which is 21, plus the amplitude, that's 9, minus the precision, that's equal to 1. Therefore, the limits here for the first class, it's 29, 21 and 29. Then the second one, that will be the lower limit for the second class, and then the upper limit for the second class. So just check the equations again. So for the remaining classes, for the lower, you just take the previous lower plus amplitude. And for the upper, that will be the previous upper limit plus the amplitude. So for the lower, then the previous lower was 21 plus 9, that's the amplitude. That will be 30. And for the upper one, is the previous upper limit, that's 29 plus 9, 38. So we have the limits for the first two classes, 21, 29, 30, 38, and you can keep going for the remaining values. So just let me show it to you here. So the class limits are 21, 29, as we just found, 30, 38, 39, 47, 48, 56, up to the last one, which is 84, 58, 92. All right, so in a similar way, now you can compute the boundaries. And remember that we use the boundaries to compute the frequencies. So for the boundaries, let me add an additional. Okay, one more page here. The boundaries now. All right. So for the lower boundary, all right. So for the lower boundary of the first class, that will be phi1 is going to be equal. And let's check the equation so you can remember here. For the first class, it's just for the lower boundary, it's equal to the lower class limit minus the precision divided by 2. And the upper one is just the upper class limit plus precision divided by 2. So let's use that logic. All right. So as I was saying, this is lower limit of the first one minus precision divided by 2. So the lower limit is 21 minus precision divided by 2, that's 0.5. Therefore, this is 20.5. And now, for the upper limit of the first class, it's going to be the upper class limit. That's L1 plus the precision divided by 2 plus P over 2. So that will be 29 plus 0.5 equal to 29.5. So these are the boundaries, the lower and upper boundaries. That's only for the first class. So now let's compute it for the second class. I'm having issues here, so let me add an extra page. I don't know why I'm having those numbers over there. They were supposed to be in the next slide. So let me just add one more page to see if I can get rid of those random numbers over there. Nope. And I cannot erase them. I don't know why I cannot even erase them. So let me see if at least I can cut them away. Nope, they're not going away. They're gonna stick with us here. That's fine. That's fine. So let me just continue here. The boundaries for the second class. So that will be I2 and FS2. All right. So for the second class, it's gonna be just the previous boundary. So that's 20.5 plus the amplitude. That's plus 9. So this is equal to 29.5. And then for the upper class boundary, this will be the previous one, the 29.5 plus 9. That's the 38.5. So we keep going using the same equation to compute the third boundaries for the third class, for the fourth one up to the last one. It's just the previous lower plus amplitude and the previous upper boundary plus the amplitude. So if we check the table, it's like this. For the first one, the boundaries are 20.5 and 29.5. For the second one, 29.5 to 38.5. So please notice that here in the boundaries, even though there is some overlapping between two consecutive classes, please notice that the upper boundary is the same as the lower boundary of the next class. So maybe you're going to be worried because it is possible in your imagination that an observation, if it's equal to 29.5, is going to be located in two classes at the same time. Well, that's not possible because remember that we use the precision and at some point we divided by precision by 2. So since we divided by 2, so we added an additional decimal. Remember that our original observations here, the original data, does not have decimals here. There are no decimals. Then by adding the precision divided by 2, we are creating that additional decimal. So in that way, we make sure that we will have an observation that's going to be located in two consecutive classes. The same applies for class 2 and 3, 3 and 4, 4 and 5. Because again, in our original observations, we don't have that extra decimal. All right, so once we have computed the boundaries, we're done. Because now it's just a matter of finding the frequencies. So now you just have to go to the original table and find for the first class how many observations in this table of the example, how many observations here are located in the first class. So how many observations are between 20.5 and 29.5. In this case, there are 4 observations. Then for the second class, the frequency is computed by identifying how many observations are between 29.5 and 38.5. So in this example, there are 12 observations that satisfy that condition. So we keep going until we have computed the frequencies for all of the classes. And in total, there are 110 observations. So this is the absolute frequency. Then you can compute the relative frequency, which is just a way to express the frequencies, but using like a percentage format. So we know, for example, that 4% of the observations are located in the first class. The class with the highest number of observations will be the fourth class. We have 25% of the observations. The eighth class, which represents the values of the variable between 83.5 and 92.5, that will be the class with the lowest frequency here. Only 2% of the observations are located within that class. So once we have the group frequency table, then we can remember that this is a way to summarize data. So now you will be able to find a histogram, for example. So the histogram is just a plot that represents a table. So it's the same information, but in a different format. So here we have the boundaries. That's the first boundary, second, third, up to the last one, up to the eighth boundary. And remember that the heights of the bars represent the frequencies. So for the first one is 4, and then the highest one, we know that it's, I think here there is something with the table because it's a little bit higher than 25. So because if this value here is 25, then the bar should be up to here. But again, it's representing pretty much the same information. There is only either an issue with the axis or an issue with the bar when I created the plot, at some point I changed some of the numbers, but they're close. They're close anyway. All right. So since we have the histogram, remember that there are other possible plots or charts that we can create. So one alternative is the polygon plot. So in the polygon plot, for each class, we take what we call the class mark. So what is the class mark? It's just the midpoint. It is the midpoint in each class. For example, for the first one, so the midpoint between 20.5 and 29.5 is 25. The midpoint between 29.5 and 38.5, that's 34. So we have the class marks here. Again, the class marks are the midpoint of each class. They are just the midpoint of each class. So in this polygon plot, when we have group data, remember that first we plot the only dots, and then we connect those dots using lines. So we locate those dots in the using as x-axis the midpoint or class mark. That's how we call it. In Spanish is marca de clase. So what we have the class mark or midpoint, again, we plot the dots, and then we draw a line so we can check if there are some trends here in our data. All right, so far we have plotted tables using absolute frequencies, but there are other plots that use what we call the cumulative frequency. So what is the cumulative frequency? It's just the frequency up to one specific class. So that means that we are going to be to accumulate the frequencies. For example, in this problem that we already solved in one of the previous sessions, remember that we use as a variable the number of failures, and the variable goes from 0 to 18. So how can we compute the cumulative frequency? So for the first class, the absolute frequency is 16, then the cumulative frequency is 16 too. Why? Because there are no previous classes. The lowest value is 0 for the variable, therefore there are no previous frequencies. So the cumulative is equal to the absolute in this case because it's the first class. But then for the second value of the random variable equal to 1, please notice that the cumulative frequency is 19. That means that if I go back to original example, the absolute frequency is equal to 3. So this 19 comes from the values of the previous frequency, the cumulative frequency of the previous values, plus the absolute frequency of this class. So it's 16 plus 3. So let me go back and show you the original frequencies. So right here, please notice for 0, absolute frequency is 16. For 1, the absolute frequency is 3. And for the variable equal to 2, the absolute frequency is equal to 9. So the cumulative values are 16. For the second class, is 16 plus 3, that's 19. And for the third class, it's the previous cumulative, so 19 plus 9. So that should be 28, right? So if I go back to the cumulative frequency table that we're creating now, please notice that the cumulative frequency for the third one is 28, as we just said. So if we keep using the same logic, you can start computing all the cumulative frequencies until we get to the last one, which is equal to 56, and that should match the number of observations in that example, which again, of course, it is 56. With the cumulative frequency, you can compute also a relative cumulative frequency, it's a percentage, and of course the last one is equal to 1. Now, when you have a cumulative frequency, the plots that you can create are different, they are not the same. So here is when we introduce the ogive plot. The ogive plot looks like the polygon plot because you have dots and you connect the lines, but the difference here is that since in the polygon plot we were using absolute frequencies, but here instead of the absolute frequency we have the cumulative frequency. So an ogive plot is always increasing, right? Non-decreasing. So it might remain the same or it will always increase. Okay, so this is one more example using one of the previous values. So this is for example 3. So for example 3, this is when we have group data. Remember example 3, a table, this one? We have group data. So using the boundaries, the upper limits are taken. So we take the upper limits, the 29.5, 29.5, 38.5, 47. Those are the upper limits of the classes. Then in the ogive plot, the dots are located in the upper limits. So we have the 29.5, 38.5. So once we plot the dots, you just connect them and you will have an increasing plot. So we will see what is the purpose of this plot later in the when we get to the Pareto chart. But just to give you an idea. So one of the usage of the ogive plot is that, for example, you can claim that the number of acceptable parts when it's equal to 74.5. So most of the frequencies, almost like 100 of the observations out of 110 are below that value, are below that value. So these are the type of analysis that you create using the ogive plot. It's like to find like what is the percentage of observations that are below a specific value, or the number of observations, or the percentage of observations that are above a specific value. So that will give you an intuition later on how to use these plots in the Pareto chart. All right, so we're almost done. Uh, I want to show you now the bivariate frequency tables, but I think I will split this video in two parts, because so far we have covered enough material. We went over the group frequency tables and some new plots, such as the ogive plot, which is a cumulative one. So I'm gonna stop here, and we're gonna talk of the bivariate frequency tables and Pareto chart in the next video. So I'm gonna stop right here.